Welcome to Lecture 9.1 on probability distribution and expected value. Today we're going to go further into looking at how to calculate probabilities and for events that aren't quite as simple as what we saw in Chapter 8. Probability has applications to quality control in manufacturing and to decision making in business. It plays a role in testing new medications, in evaluating DNA evidence in criminal trials, and in a host of other situations. Sophisticated counting techniques are often necessary for determining probabilities used in these applications. Probability distributions enable us to compute the average value or expected outcome when an experiment or process is repeated a number of times. These distributions are introduced in Section 9.1 and used in Sections 9.4 and 9.6. The other focus of this chapter is the development of effective ways to count the possible outcomes of an experiment without actually listing them all, which can be very tedious when large numbers are involved. These counting techniques are introduced in 9.2 and are used to find probabilities throughout the rest of the chapter. Probability distributions were introduced briefly in Section 8.4. Now we take a more complete look at them. In this section, we shall see how the expected value of a probability distribution is a type of average. A probability distribution depends on the idea of a random variable. So let's begin with that. A random variable is a function that assigns a real number to each outcome of an experiment. So before we just said, that the outcome was to you flip a coin and you get a head or a tail. Well, now we have to assign a number to those, to that outcome, not just saying it's one head or two heads, whatever. We have to figure out a number that we can apply to that. And it should make some intuitive sense. And usually what it does is it goes off of the question, like what is the probability of tossing two coins and getting two heads? Something like that. So in that case, the intuitive thing would say the number of heads, because that's the question, what's the probability of getting two heads? The number of heads would be the actual number that you would assign to it. So let's look at some examples. One of the questions asked in the 2010 National Health and Nutrition Examination Study, NHANES, has to do with respondents' daily hours of TV or video use. The answer to that question, which we will label X, is one of the numbers 0 through 6, corresponding to the number of hours of use. Since the value of X is random, X is called a random variable. So here you can see the following table gives each possible outcome of the study questions on TV and video use together with the probability, P of X, of each outcome. So you can see here, these are the random variables. This is, I watch 0 hours of TV, I watch 1 hour, 2 hours, 3, 4, 5, 6. Okay. Below it is the probability. So there's a 0.13 probability that when you're surveying someone, they will watch 0 hours of TV. There's a 0.07 probability that they watch 5 hours of TV. A table, like the one you see here in blue, that lists all the outcomes with the corresponding probabilities is called a probability distribution. The sum of the probabilities in a probability distribution must always equal 1. The sum in some distributions may vary slightly from 1 because of rounding. Okay, so remember this, if these are all our possible outcomes, then the probability of each outcome summed together has to be 1, right? Because these are our only possible choices, so it has to be one of the 6 or 7 choices. So if we add all these up together, then we have a certain event, which is probability equal to 1. All right. The information in a probability distribution, here's our probability distribution from the last problem, is often displayed graphically as a special kind of bar graph, which you can see up here to the right, called a histogram. The bars of a histogram all have the same width, usually 1 unit, And the heights of the bars are determined by the probabilities. Okay, so you can see here we have really the random variables, and then here we have the probability of each of those. And this was again based on the number of hours people watch TV. Give the probability distribution for the number of heads showing when 2 coins are tossed. So let's go back to some of our prior knowledge and think about if we toss 2 coins, what are the possible outcomes? We can have heads, tails, tails, heads, 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 and tails, tails. Since we're looking for, we have to assign a variable, a random variable. Here we're going to use the number of heads because we're looking for the distribution for the number of heads, so it's very intuitive. And then again, here's our sample space for this event of throwing 2 coins, right? We can do tails, heads, tails, 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 heads, heads, tails, and heads, heads. All right. So what are how many different numbers of heads can I do? Well, here I have 2 heads. Here I have 0 heads. I have 1 head, I have 1 head, I have 2 heads. So it's possible to, when I toss 2 coins, to have 0, 1, or 2 heads. I can't have 3 heads. So those are going to be my X values in the chart. When I toss 2 coins, I can get 0 heads, I could get 1 head, or it's possible I could get 2 heads. Okay. Now, what's the probability of throwing 0 heads, of tossing 0 heads? Well, you know that. It's the number of outcomes in the event divided by the number of outcomes in the sample space. Well, the sample space has 4 items. What is the outcome that has 0 heads? Well, there's only one, tails, tails. So my probability for 0 heads is 1 out of 4. There's one event, tails, tails, which gives me 0 heads, and that only happens 1 out of 4 times in the sample space. See if you can do the probability that when I toss 2 coins, I'll get 1 head. Well, there's tails, heads, and heads, tails. That's 2 different cases, 2 different occurrences out of 4, so 2 out of 4. 2 heads, that's heads, heads, that's 1 out of 4. And so we get our probability here. Okay? This is our probability distribution for the number of heads showing when 2 coins are tossed. B, draw a histogram for the distribution in the table. Remember, your y-axis is your probability, and your x-axis is your random variable. And this even looks like notation, right? X and then y, a function of x. All right. It also asks us to find the probability that at least one coin comes up heads. Now be careful. Remember that when we do these things where we say at least one or at most one, we have to be real specific. At least one coin comes up heads means that we either have the probability of 1 head or the probability of 2 heads, right? And so our probability of 1 is 1/2, and our probability of 2 heads is 1/4, so we simply add them together and get 3/4. Okay? Remember, when you're doing these, the descriptions are not exact, like at least, at most, greater than or equal to. Then you have to be precise and list the cases. In working with probability distributions, it is useful to have a concept of the typical or average value that the random variable takes on. In example 1, for instance, it seems reasonable that on the average, 1 head shows when 2 coins are tossed. This does not tell what will happen the next time we toss 2 coins. We may get 2 heads, or we may get none. If we toss 2 coins many times, however, we would expect that in the long run, we would average about 1 head for each toss of 2 coins. A way to solve such problems in general is to imagine flipping 2 coins 4 times. Based on the probability distribution in example 1, we would expect that 1 of the 4 times we would get 0 heads, 2 of the 4 times we would get 1 head, and 1 of the 4 times we would get 2 heads. The total number of heads we would get then is 0 times 1 plus 1 times 2 plus 2 times 1, which equals 4. The expected number of heads per toss is found by dividing the total number of heads by the total number of tosses, or dividing this by 4, and of course we get 1. So here we can also see it, 0 times 1/4, 1 times 1/2, plus 2 times 1/4 equals 1. Does this look like anything or remind you of anything from our example before of tossing 2 coins? Well, let's look. Remember that our probability distribution for tossing 2 coins and calculating the probability of the number of heads is up here in the right corner. The expected number of heads per toss is 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. So if we take the random variable and multiply it times its specific probability, and then sum all of these together, this is what we have here. And that's how we get the expected value. It's the random variable times its respective probability, and then sum all of the random variables times their respective probability. Notice that the expected number of heads turns out to be the sum of the 3 values of the random variable multiplied by their corresponding probabilities. We can use this idea to define the expected value of a random variable as follows. Expected value. Suppose that the random variable can take on n values, x sub 1, x sub 2, x sub 3, etc., all the way up to x sub n. Suppose that the probability that these values occur are respectively p sub 1, p sub 2, p sub 3, ... up to p sub n. Then the expected value of the random variable is x sub 1, p sub 1, plus x sub 2 times p sub 2, etc., all the way up to x sub n times p sub n. This is a very important formula for you to remember. You need to know this expected value formula, which is simply taking the random variable times its respective or corresponding probability in our probability distribution and adding them all together. In the example with the TV and video usage on page 466, find the expected number of hours per day of viewing given the following probability distribution. So go ahead and try this problem, hit pause, and see if you can calculate this problem. So of course we get 0 times 0.13 plus 1 times 0.24 plus 2 times 0.33 plus 3 times 0.14 plus 4 times 0.07 plus 5 times 0.07 plus 6 times 0.02. When we sum these all together, we get 2.07. Now what does this mean? Well, go back to your question. What was the question about? What was the table about? The expected number of hours per day of viewing. So what we can say is, in general, we would expect that someone answering this survey would view TV for 2.07 hours. On average, respondents watched 2.07 of TV or videos per day. So this is expected value is kind of an average. It's kind of the middle point of your probability that kind of allows us to know what's likely to happen. This is a really interesting question, and it's got some really good thinking involved in here that's, a little bit hidden. Suppose a local symphony decides to raise money by raffling off a microwave oven worth $400, a dinner for 2 worth $80, and 2 books worth $20 each. A total of 2,000 tickets are sold at $1 each. Find the expected value of winning for a person who buys 1 ticket in the raffle. So what we're looking for is the expected value of winning. So our random variables are going to be about us winning. What do we win? How much do we win? Remember, random variables are actual numbers. Okay, so what's possible to win in here? Well, we can win a microwave oven, we can win a dinner for two, or we could win two different books, either each worth $20. So we have microwave, we have a dinner, and we have books. We also have something else. What's that something else? Do you know? What else is possible to win? Nothing. You could win nothing, right? So here's the tricky part. Well, wait, you're like, wait, the microwave was worth $400. That's correct, but remember you paid $1 for the raffle ticket. The dinner for two is worth $80, but you paid $1 for it, so you're really only winning a value of $79. Each of the books is worth $20, and so if you won a book, you would win essentially $19. And of course, if you won nothing, then you would actually lose $1, and so that random variable is a -1. Now, how do we figure out the probability for winning the microwave? Well, how many microwaves are there? 1. How many tickets are sold? 2,000. There's one winning microwave ticket for 2,000, so it's 1 over 2,000. What about the dinner? Again, we have one dinner for two. Don't be confused. It's a dinner for two. So we have one winning raffle ticket out of 2,000. What about two books? Well, here we have two winning tickets because we're giving away two different books out of 2,000. And then what about winning nothing? Well, how many people are going to win nothing? Well, how many prizes were there? 1, 2, 3, 4. So here we'd have 2,000 minus 4, which is 1,996 out of 2,000. So the probabilities are pretty simple to calculate logically with a little bit of thinking, but you also have to remember in these kind of raffle things or winnings that you put some money in order to play the game, and you need to deduct that out of your winnings, whatever the value of the winning was. So now we're really ready to find the expected value. Now it's a simple calculation. 399 times 1 over 2,000, 79 times 1 over 2,000, 19 times 2 over 2,000, and -1 times 1,996 over 2,000. And when we do that, we get -0.74. Again, what does that mean? Remember, we're talking about winnings. Find the expected of winning for a person. Well, this is -0.74. So what does that mean? On average, a person buying one ticket in the raffle will lose 74 cents. 0.74, remember, we're talking about money, so it's 74 cents. So we were looking at this problem. We figured this out that on average a person will lose 74 cents. Well, it's really not possible to lose 74 cents in this raffle, right? You will either lose $1 or you'll win a prize worth 480 or 20 minus the $1 you paid. But if you bought tickets in many raffles over a long time, you would lose 74 cents per ticket on average. It is important to note that the expected value of a random variable may be a number that can never occur in any one trial of the experiment, because again, it's an average value, not necessarily a realistic outcome for one specific individual or event. Let's try another one. Let's see if you can build this one out. Each day, Lynette and Tanisha toss a coin to see who buys coffee at $1.75 a cup. One tosses while the other calls the outcome. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find Lynette's expected winnings. So here we have a tosser and a caller, okay? So it really doesn't matter which one we make, Lynette. But we need to build a distribution table for the caller winning and calculate the expected value. So notice when we toss, we could toss a head and the person could, we could toss a tail and the person could say head. We could toss a tail and the person could say tail. We could toss a head and the person say head, or we could toss a head and the person say tail. So these are all the possible outcomes, okay? Now remember our random variable is, what are we looking for? Find Lynette's expected winnings, okay? So let's assume Lynette is the caller. So the caller wins a cup of coffee, $1.75, if they match the call. So in this first case, the random variable, the caller doesn't match, so they're actually going to lose $1.75, so this would be negative 1.75. Here, the caller matched the toss, so they would be a positive 1.75 because they get a cup of coffee. The next one, the same thing, it matches, so they get a $1.75 coffee value. And the last one, they don't match, so the caller would lose $1.75. Well, all of these cases happen 1 out of 4 times, right? There's no duplication here. So this is one event out of 1, 2, 3, 4. So now we can apply the expected value formula by multiplying the random variable times the probability and calculate. Well, this is interesting. It came out to 0. What does this value mean? On the average, over the long run, Lynette will break even. Lynette will break even. This is what's called a fair game, that the two people playing over a long period of time, they will break even. They will win half as many times as they will lose, okay? When you have a expected value of 0, this is a break-even point. A game with an expected value of 0, such as the one in example 4, is called a fair game. Casinos do not offer fair games. If they did, they would win, on the average, $0 and have a hard time paying their employees or subsidizing the free drinks. Casino games have expected winnings for the house that vary from 1.5 cents per dollar to 60 cents per dollar. The next example examines the popular game of roulette. As we saw in Chapter 8, an American roulette wheel has 38 slots. 2 of the slots are marked 0 and 00 and are green. The remaining slots are numbered 1 through 36 and are colored red and black. 18 slots are red, 18 slots are black. One simple wager is to bet $1 on the color red. If the marble lands in a red slot, the player gets his or her dollar back plus $1 of winnings. Find the expected winnings for a $1 bet on red. Okay. So here we're going to roll. We're going to bet on red, and we're looking for the expected winnings. So if I bet on red and it comes up red, I win $1. If I bet on red and it comes up black or green, then I lose $1. So really in this case, our probability distribution is either win or lose, right? It either lands in black or it doesn't. So we only need 2 columns there. Our variable, if we lose, we're going to lose the $1 we bet. If we win, we're going to get our original $1 back plus an additional $1. So we're actually increasing our win by $1. Now, how did we get this? If we lose, remember there's 18 red slots and 18 slots are black, but there's also 2 more that are green. So if it lands, there are 20 non-red slots out of 38. So that's the probability we will lose. And there are 18 red slots out of 13. So again, if it lands there, we will win. So our probability, our expected value, our average probability is negative 0.053. See if you can determine what this means. On average, a person betting $1 on red will lose 5.3 cents. The winnings on a dollar bet for red average out to losing about a nickel on every spin of the roulette wheel. In other words, a casino earns, on average, 5.3 cents on every dollar bet on red. The following table gives the probability distribution for the number of children of respondents to the 2012 General Social Survey for those with 7 or fewer children. Find the expected value for the number of children. Now, this is the easiest type of problem from this chapter because you know the formula for expected value is simply multiply the random variable times its corresponding probability and then add them all up together. So go ahead and try this problem, hit pause, and then see if you get the right number. You should get 1.818. Okay, so on average, a family with 7 or fewer children has 1.8 children. Weird, I know, but that's kind of gives us some insight. All right, that's the end of our lecture. Hopefully this is helpful to you, and that if you have any problems, please feel free to reach out.